Hi everybody, this is Professor LaShan, and I am going to go over an example from section 9.1 and 9.2 from the course lecture notes. So in the course lecture notes, I have example 1, which is not from the textbook, but it talks about the age of child being X and the youth shoe size being Y. And so I'm going to go through that example and calculate R, the correlation coefficient, sample correlation coefficient, and then also make a regression line equation from that data, and then looking at that on a scatter plot, what does that look like? Again, you could calculate all this stuff using software, using in MyStatLab using StatCrunch. You can use a graphing calculator. You don't have to do these calculations by hand, but in case you want to, I'm going to walk through that process using this example. The ones in the book are a little bit more complicated, so I wanted to use numbers that were easier to walk through. So walking through that, looking at this example, X, so we have 8 data pairs, so that's our sample size, 8, that's N. X, the independent variable, is age, and Y, the dependent variable, is shoe size, because shoe size of the youth depends on the youth's age. As someone gets older, their shoe size gets larger. And so it's not the other way around. Age doesn't depend on shoe size. So that's why X is age, Y is shoe size. It's the dependent variable, Y. So we're going to take these 8 pairs of values that are given in that example from correlation example 1 here, written them on my board here, my whiteboard, and now I'm going to use those to hand calculate R, the sample correlation coefficient. This formula that I gave in your formulas page for chapter 9 is just a more easier format of the formula versus the really long way they have it in the textbook, where you just break it into pieces. We find the sum of squares of X, the sum of squares of Y, and the sum of squares of XY, and then put them into this formula to calculate R. It makes it a little bit easier. So when we're going to do this formula here, we make this table here. And so we're going to make columns of X, which was the age, Y, which was the shoe size, X times Y, X squared, and Y squared. And so we've got our 8 values for X, and we have their sum, which is 90. We have our 8 values for Y and their sum, which is 28. We have X times Y, 8 times 1, 9 times 2, and so on. And this column, that sum is 343. We have each of the X values squared, 8 squared, 9 squared, 10 squared, and so on. That sum is 1050. And we have each of the Y values squared, 1 squared, 2 squared, and so on. That sum is 120 of Y squared. So we're going to use those values, those sums that come from that table, and the value of N equals 8 to calculate R, the sample correlation coefficient from our sample. So we're going to go to our formulas here. And so going to the formulas page, it says the sum of squares of X is the sum of the X squared column minus the sum of the X column squared over N. So from our previous board here, we found that the sum of the X squared column was 1050 minus the sum of the X column was 90. We're going to square that and divide by 8, which is N. So we're going to go to 1050 minus 90 squared, 8100 divided by 8. So you could probably put this version of the formula in your calculator if you want, and it'll give you the right answer. Or you could then do 90 squared is 8100. You could put this in your calculator, 1050 minus 8100 divided by 8. It should do it correctly, order of operation, and give your sum of squares of X as 37.5. For the sum of squares of Y, our formula is the sum of Y squared minus the sum of Y squared over N. So the sum of the Y squared column was 120 minus the sum of the Y column was 28. We're going to square that and divide by N is 8. So that's 120 minus 28 squared is 784 divided by 8. You can put that into your calculator, or you could have put this version in, it would work too. And the sum of squares of XY will be 22. And the third thing we're going to calculate individually is the sum of squares of XY. Again, all this from that formulas page I gave you. So that's the sum of the XY column minus the sum of the X column times the sum of the Y column divided by N. So the sum of the XY column is 343. minus the sum of the x column 90 times the sum of the y column 28 over n8. I'm doing this multiplication here. 90 times 28 gives you 2,520. You could put this into your calculator, 343 minus 2,520 divided by 8, and that should give you the sum of squares of x, y, which is 28. So taking those three values for the sum of squares of x, sum of squares of y, and sum of squares of xy, we're going to put that into this formula here for r, again on the formulas page for chapter 9. So doing that calculation, we have that here. So we have the sum of squares of xy, which is 28, divided by the square root of the sum of squares of x, 37.5, times the sum of squares of y, 22. So I'm going to do that multiplication. So that's 28 divided by the square root of 825. You can put this directly in your calculator. You could also take the square root of 825, which is, I don't know, 27 something like that. No, I guess it's like 28 something maybe, 28, 29 something. But I just put this in my calculator directly, and I got my R value of 0.9748 something. So generally you carry about 3 decimal places for your R value, your sample correlation coefficient. So it's 0.975, since in the thousands place is a 4 and in the 10,000th place is an 8, we'll round up. So that's a very strong positive linear correlation. The strongest positive one would be +1, and that's really close to +1, which means if we make a scatter plot of the data, it should be kind of close to a straight line increasing, because going up, because the R value is positive. So positive linear correlation. So if we look at that, if we take that data, which was given in the original example, these values here, and we plot them. So x, I made a little break here, goes from 8 to 14. Y goes from 1 to 6. And I plotted these values in purple. Ignore the green and the red points for a second. We'll come back to that in the later examples. So if I plot 8, 1 in purple here, 9, 2, 10, 2, 10, 3, 12, 4, 13, 5, 14, 5, and 14, 6. The ones in purple, there's my scatter plot. And you can see it's a pretty linear correlation if you look at those purple dots. It's pretty close to a straight line positive linear correlation, which then backs up the fact that we calculated our R value to be very close to +1, 0.975. So now going to the next bit of this example, we're going to calculate the regression line, which is what we did in section 9.2. Again, I'm going to my chapter 9 formulas that were given in the chapter 9 formulas page for M and B. And we're going to use those formulas to calculate our regression line. So a regression line is the equation y hat, or expected y, equals mx plus b. As you all remember from algebra, a straight line has an equation y equals mx plus b, where m is the slope and b is the y-intercept. So our formula for m from our formulas page for chapter 9 and for b are here. So our formula for m is n times the sum of xy minus the sum of x times the sum of y over n times the sum of x squared minus the sum of x squared. So again, we're going to go back to that table we made to get all of these values for these numbers here. And remember, the sum of x was 90, the sum of y was 28, the sum of xy was 343, and the sum of x squared was 1050. And we'll use the sum of y squared in a minute here, 120. So putting in these numbers, 8 times the sum of xy, 343, minus the sum of x, 90, times the sum of y, 28, over n, 8, times the sum of x squared, 1050, minus the sum of x, 90, squared. So calculating 8 times 343, you get 2,744, minus 90 times 28, 2,520. 8 times 1,050 is 8,400, minus 90 squared, 8,100. So then doing those subtractions, we're going to get 224 divided by 300 which if you divide that out, you get 0.7466 approximately. So again, rounding to about 3 decimal places, our slope is 0.747. And that makes sense, again, because if you look at our line, if we're our points, and we're going to draw a straight line in a minute here, it's got a positive slope. So the m value should be positive. If the points were going down and it had a negative correlation, the slope would need to be negative, but it should be positive, which it is here. Change in y over the change in x. Okay, so next we're going to calculate the b value, the y-intercept. So that is the centroid value. It's the mean of y minus m times the mean of x. Using those centroid, x bar and y bar, mean of y, mean of x, we're going to use that to calculate b and m. So we're going to take the mean of y, which we know is the sum of y divided by n, minus m times the mean of x, the sum of x divided by n. So remember, we got the sum of the y column was 28 divided by 8, gives you 3.5. Minus m was 0.747 from above here, and we just got that, times the sum of x, which was 90 from our table, divided by n8. So doing the divisions, 28 divided by 8 is 3.5, minus m, 0.747, times the mean of y, 90 divided by 8 is 11.25. So if I do this multiplication of 0.747 times 11.25, I'm going to get 8.40375. So when I do this subtraction, I get my y-intercept of negative 4.90375. That's our b value. And rounding to about 3 decimal places, we'll call that negative 4.904 for our y-intercept. So our regression line, y hat equals mx plus b, or expected y equals mx plus b, is y hat, or expected y, equals 0.747x plus, or you could say minus, 4.904. So that's what we're going to use on the next section here to then do some expected values for y given an x value. So last one here. So first thing we have to do is calculate what's called the centroid value, which is the point that the line will always go through. That's the mean of x, mean of y, and we just found that above, that the mean of x was 11.25, the mean of y was 3.5. So if we go to our graph here and we were to plot this point, 11.25, 3.5, and I did that in red, I went right 11.25 and up about 3.5. That's this point in red. So our line of best fit should always pass through this centroid point here, x bar, y bar. And so that's an important point. And again, I'm not super accurate, sorry, with my graph, because I don't have graph paper here to do this on my whiteboard, but I'm doing my best. So now we're going to say, what if we have an x value, for instance, of 11? What if you have an 11-year-old? And that wasn't in the original data. In the original data, we didn't have an 11-year-old. So what size shoe would an 11-year-old wear approximately? So if we go to this formula here, and we take our formula for expected y and we replace x with 11 and multiply by 7.47 and then subtract the 4.904, we would get that an 11-year-old would wear about a size 3.3 something. So a little bit more than a size 3, going into a size 4. Shoes are getting a little tight here. And then let's do one more, and then we'll talk about how that works with the line here. And so what if we have a 6-year-old? Well, that's a problem actually, because in our original data, if we go back and look at the data, this data is meaningful for age 8 to 14. So if you have a 6-year-old, they probably don't wear a youth shoe size. They wear a child's shoe size. Those of you who have young children probably remember that. So this isn't meaningful for a 6-year-old. So we actually can't use that equation to predict what size a 6-year-old would wear. It's only meaningful for youth shoe sizes from 8-year-olds to 14-year-olds, because that's what we have here in our data. So it's not meaningful because the value of x is 6 is outside the range of our x values, or the allowed values for our x values, which are meaningful. Okay, so let me stop here and I'm going to do another video.